Welcome to Calculus. We conquer our fears and flex in the face of adversity. On this episode, Stevenson will demonstrate
how would you define the word implicit? Weird, right? Think for a moment. What does it mean to you? Well, I want you to take that idea that you have in your head right now, and we're going to take it and we're going to apply it mathematically. So when we talk about something that's implicit, we think of something that's hidden, it's implied, it's not clear, explicit. It's something that's not direct, it's more indirect, okay? So kind of keep those ideas going on your head here. So I'm going to give you 3 graphs, and I want you to think to yourself, what do F, G, and H all have in common? Now, hopefully you can look at them and realize they all are considered one-to-one. In other words, they would pass the vertical line test. And what that means is that they each would have a derivative that would be unique for a specific x value. For example, if we looked at f of x, and I said, find the derivative at this particular x value, so you can see the purple dot there, and it's showing that it's the x value, it's the input, we can see that there would be a particular derivative. And I could pick another x value, and that's by the other dot right here. And you can see they would each have their own unique derivative. In other words, because they're one-to-one, I can find the derivative and give you an x value, and then you would tell you what the derivative is coming out. The same is true for g or h. So g, if I picked a value there, or there, or there, again, I could get one derivative value based on one x value because it's a one-to-one function. Now let's look at h of x. Again, this is periodic, same thing happens. A few more examples there for you. So in other words, if you pick an x value and draw a line through it, a vertical line, it'll cross your graph only one time. Okay. Now, what do these graphs have in common? Hopefully you recognize these are not one-to-one functions. They will not pass the vertical line test. These are what we call implicit functions. In other words, they are relations that are combinations of both x of y of other functions. So remember in the beginning when I asked you, what does it mean for something to be implicit, right? It's implied, it's hidden. Well, let's look at the circle, for example, k of x. The circle is actually made up of 2 separate functions. This is the general equation of a circle centered at the origin. Now, this particular circle isn't really centered at the origin, but I'm just using that formula to make a point. If you were to solve that for, say, y value, you would actually end up with 2 answers, because this can be broken up as an above and below piece, or an upper piece and a lower piece. So if you solve that equation, that x squared plus y squared equals a squared, you're going to end up with y equals radical a squared minus x squared as the upper piece. Then, if you do the same thing, you're actually going to get the same answer, but the difference is the radical is negative. Why? Because when you take the square root, what do? You get a positive and a negative. So the positive radical represents the upper half, and the negative radical represents the lower half. The same thing is true for this one down here, j of x. J of x is actually a sideways parabola, and its equation, or its general form, is what you see before you, x plus y squared equals a squared. A is just some constant, by the way. That's true for this setup here. So if you solve for y squared, again you end up with 2 answers, one for the above piece, one for the below piece. And again, the above piece would be the positive radical, and the below piece, or lower part, would be the negative radical. So these graphs are represented by some function essentially, but it's implicit, meaning they're actually composed of 2 other pieces together. M of x follows a similar path. With m of x though, it would just be broken up into 3 pieces. And again, they would have 3 unique equations. I didn't take the time to make those, but hopefully you get the point by this slide. Remember when we talked about derivatives, right? So now that we realize the k of x, j of x, and m of x are not one-to-one, but they're implicit functions. Well, how does that impact our ability to find derivatives? Well, we know k of x, for example, is a circle, and it's going to be composed of 2 parts. Well, when you go to do its derivative, what this means is you can't use just a single x value. You have to use an actual ordered pair to evaluate the derivative. So at the bottom there, you can see you need to actually use an xy coordinate. Now you may be asking, why, Stevenson? Why can't I just use a single x? Well, let me show you. So let's focus on the circle. Suppose I wanted to find the derivative and I just said at x equals -4. You may be wondering, what's the harm? Why can't I just plug it in? Well, watch what happens. If I plug in -4 for my derivative, do you notice it actually goes through that vertical line goes through my function 2 times? So we have a problem. It created 2 different derivatives. How do you know which derivative you're referring to? The only way to distinguish between both of them is you need a y coordinate. So what this means is that when you go to evaluate a derivative of an implicit function, you must use an ordered pair. I'll say it again. In order to evaluate an implicit derivative, you must have an ordered pair. You cannot use just the x value. This is true for all of them. So let's look at j of x. If I pick that red dot that just popped up there and I draw a line through it, do you see how I'm going to get 2 different derivatives? Same thing's going to happen at m of x. There's my point I'm picking. Notice it touches 3 different times.